All right, guys, this is November 2023 exam that we are going to take a look into before our examinations that we can at least have something that we can use on our revisions. So we were given that is going to try to have this, the full paper. So let us consider the first part of our question, which is 1.1. We're given to start, give 5 characteristics of a batch production. All right. So when you're dealing with a batch production, what are the characteristics that you are going to need on that? That is the part of our question. So we need, these are the things that you're going to need. There is a moderate demand for the product. All right, the production is broken down into a number of different operations. Also, a limited number of items are produced at a time. So just a limited number of items, and the volume of production is lower than the mass production. There is a degree of standardization between each item in a batch production is identical. So there is a degree of standardization there, and because each of the item there that we have is identical. So that is the major part that you are going to need when dealing with a batch production. So 1.2 is name 5 advantages of airless spray painting. All right, when dealing with an airless spray painting, sometimes they might need you to draw the diagram of this, but here they need just advantages. All right, so it reduces overspray, less solvent is needed, and the overhead spray painting is possible. Also, air pockets are limited, eliminated, allowing uniform coverage on uneven surfaces. Then the paint container holds a large quantity of paint. That is what you are going to need in that case. All right, then 1.3 was to make a neat labeled sketch of a needle feed lubricator. That is a needle feed lubricator. So this is what you are going to have at the end. All right, so it's something like this. You have in your bearings, shaft, oil, the needle resting on the shaft, and also the oil container. So with this, you are going to obtain 5 marks, just to indicate that. 5 marks, which is 15 marks on question number 1. All right, so I'm not much worried actually on this part of our number 1. Yes, it's important that you do revise your theory, because you're going to need something like about 15 marks or 20 marks at the end of the day. So you need to know your theory part. So question number 2, let us consider this. I think from the introduction of our precision measurement, we had a similar diagram also like this. So I hope now you understand whenever you're given this. So this was 15 marks, just to calculate from the neat construction, the distance across the top and the bottom rollers. All right, so we've got the distance on top, which is Y, and the bottom, which is X, on these rollers that you're given. So this is what you're given there, that fig 1 below shows a taper of 1 in 5. Take note, we are given a taper of 1 in 5 on a diameter that must be tested for correctness by using 18mm diameter rollers. So these diameters that we are given, they are of diameter 18 millimeters. The center distance between the top and the bottom, 55 millimeters. So this is the top distance, 55, and this other height, 80 millimeters, which is the taper is 80 meters long. The top diameter of the taper is 50 millimeters. At the top, the diameter is 50 millimeters, and at the bottom, we do not have the diameter. In this case, from this point to this point, we do not have the diameter. We're given the diameter of the top. So that was our information. As you can see, it's clear. Then calculate from a neat construction the distance across the top and the bottom rollers. All right. So let us consider the first thing that we have got a taper, which is 1 in 15. What is the purpose of this taper? The purpose of the taper is that we can calculate the included angle from there. I referred to this on our introduction, that you are going to have actually just a piece of a diagram like this, whereby the taper that you are given of 1 in 15, it is indicating that of 1 in 5, it is indicating that from there we've got 1 and this is 5. So 1 is divided into 2 equal parts, so it will be 0, 0.5, 0, 0.5. We talked about this. So what you're going to do is to calculate alpha, which is this angle, then the whole of this angle, which is our theta, which is our included angle. So theta, the included angle, is equal to 2 alpha. So that means I have to calculate alpha from a right angle triangle. This is our opposite, and this is adjacent. So we need a ratio that consists of the opposite and adjacent at the same time, which is the ratio of a tan. The tan of alpha is opposite 0, 0.5 over the adjacent, which is 5. So that means alpha is going to be arctan 0, 0.5 over 5. So that is going to give us alpha in that case, and that was going to give you something like 5,711 degrees. With the angle alpha, therefore, the included angle theta can be calculated, which is 2 times alpha. That is 5,711 degrees. All right, so that's our theta is going to be 11,422 degrees. So that's our theta, which is the included angle in this case. So you're going to need this angle. Also, you're going to need alpha in your calculations. So take note about these angles. It's not like that we are just calculating for something. No, we are calculating this that we are going to need. All right. So let us consider this, guys. We need to calculate x and we need to calculate y. So to calculate x or to calculate y in this case, we are going to need this distance at the, the diameter at the bottom part here, this diameter at the bottom. So what is going to be the value of the diameter at the bottom? We need this diameter because we're going to need this diameter at the end. All right, so let us consider to calculate the diameter. In this case, we've got a lot of things that we have in this case. All right, this is going to limit us. Let us consider with the top. So if we consider the 50 is covering this, the 50 is covering the diameter here. It is also part of this diameter. The 50 is an extension to the other part of our diameter. So let me present this way. I think we can win. All right. If we take it this way, straight, I'm just going to take it up to this point here. Straight up to this point, and also straight up to this point here. I talked about this from the previous, from our introduction. So we are going to see that the 50 here, it carries our diameter, which is this one. It carries the diameter. If we take it a closer consideration, you're going to see that the diameter is also involved at the bottom. All right, so we can use that 50 to calculate the diameter first, then we can calculate x. Guys, it's a stage. These are the steps that you need, but I just hope you still remember those steps that we talked about. So the first thing, let us find, in this case, the diameter. Find the diameter on the bottom, or at the bottom, So this is, I'm just gonna refer it as the small letter d, like that. So this is going to be given as what? That is including from the 50 that because we are going to calculate from the 50. So let's say this point, I'm just gonna call it point A, which refers the same thing as the side. I'm not gonna like use many points, guys. This is like the same thing as this side. So if this is B, let's say this is C, which is the same thing. Like this side from B to C is just the same thing, like B to C. You can use any other letters, guys, which is fine. But I do not want like to have the like repetitions, guys. Like to have different things representing the same thing. From here, from this point to this point is the same as from this point to this point. So I'm just going to call this BC, this one. Is this the same thing? So if we are to take a closer look, 50, it consists of the BC and this D, which is the diameter at the bottom, which is the same as this length from here to here, and also this one. They give us the 50. So let us consider that 50 is the sum of those three that is 50 is equal to BC. So you're going to take BC plus the diameter at the bottom plus also BC, which is this one from this point, like this point is the same thing. You can name it R, you can name it whatever letter that you want. So here I just want to use the same thing so that we do not have a confusion. So the BC is the same thing. So that means here I'm just having 50 is equal to BC plus BC, which is 2BC plus D. So that means to find D, I'm going to have 50 minus 2BC. So that's I'm having an expression that I'm going to use to calculate the diameter at the bottom. So the moment I calculate BC multiplied by 2 times because it's the same. The BC here is the same as this one. It's just only the same thing. So where do we have BC? That is the question. Are we able to calculate BC? All right. Let's consider this. We are given, in this case, we can calculate this because that alpha that we calculated here, this alpha here is the angle between the points here, this one. It is the angle between the taper. That is this angle here is your alpha. So we have got alpha. We have got alpha. Remember our alpha was the angle of 5, we got this angle is 5,711. So this is 5,711 degrees. So we can actually calculate BC because this length, we have it from A to B. This whole length that we have is this one, length of the taper, which is 80 millimeters, the whole of this length from this point up to this point. This is the same as the 80 millimeters. So meaning to say we've got 80 millimeters, which is the length. So we can calculate BC in that case. All right. So in this case, we can calculate our BC. We are going to have something like this. If you check properly, you can take the other side. You can take whatever side that you want. You can use this triangle or you can use this triangle. It's one and the same thing. They are concurrent triangles. So from this case, we saw that you're just going to have a triangle like this. All right. Sorry for that, guys. Okay. So that's the problem with these things, guys. And I wonder why is this thing giving me like these centimeters that you are seeing here. But anyways, we're going to have something like this. So this is from the triangle, this one from A to B to C. So this is our A, this is our B, this is our C, and it's a right angle triangle. And you said from A to B is 80 millimeters. And this angle is our alpha, not theta. Theta is the angle, the included angle. But we need alpha, that one from your taper, all right? So that was 5,711 degrees. So you can calculate BC, which is this side here, according to this angle that you are given. This will be your opposite, and AB is going to be the adjacent. So that means according to the ratio of tan, the tan of theta, 5,711 degrees, is equal to the opposite, which is BC, over the adjacent, and the adjacent is 80 millimeters. So that's it. We can calculate our BC. 1 times BC, if we cross multiply, that's going to be BC is 80 times the tan of 5,711 degrees. So that's it. We are going to have our BC in this case. So 80 times tan is going to be approximately 8 millimeters. If you round off to, it's going to be approximately 8 there. So this is what we have now. We have got BC, so that means we can calculate the diameter at the bottom, because from this equation that we are having here, it states that the diameter is simply equal to 50 minus 2 times BC, because BC is the same both on the diagram that we are given there. So this was going to give us the diameter at the bottom, which is 34 millimeters. We have the diameter at the bottom, and what is the purpose of having or to calculate this diameter at the bottom? What's the purpose of knowing that this is 34 millimeters from this point up to this point? What is the purpose of knowing that it is 34 millimeters? Okay, with this information that we have used to calculate this diameter at the bottom, we are going to see that it was necessary to have that, because to find x, so let us try now to find x. So to find x, which is the distance at the bottom here, we are going to see that x is a combination of a lot of things at the bottom here. X, it is a combination, a distance from this point up to this point. That is where our x is. So if we take a closer consideration, we are going to see that this x that we are talking about from this point up to this point here, it is consisting of from this point up to this point, which is this distance here, is the radius. We are at the circumference of the circle to the center of the circle. So it consists of the radius there. So there is a radius which you're talking about. All right, then there's a distance that you can take from this point up to the point A. It's no longer the radius because it has overlapped the circle. As you can see, it's no longer a radius. It's no longer a radius. But if you take this distance from A to the origin of the center or to the center of the circle like that, you are going to see that you are formulating there. This line that you are having is a tangent. So we are formulating a right angle triangle because this is a radius, and we know that a radius and a tangent, they meet at what? At 90 degrees. So this is a tangent. So this is a radius from the center. We've got a radius. So these two, they meet at 90 degrees. And also about the angle that we had. Okay, we're going to talk about that. Remember, this angle that we are having is alpha. The angle in between here is alpha. So meaning to say, if you subtract this from 180 degrees, you're going to have this angle that is remaining here, the alpha minus 180. Okay, let's just finish about this. We can just work with one side, which is fine, like that. All right. So remember, this angle was alpha, this one. This is alpha, this angle that is in between this one here, the angle covered here, inside here, this one. It is our alpha, this one. And this alpha is 5,711 degrees. Okay. So what I'm simply saying is that if we are to subtract from 180, because this is a straight line, all right? This is a straight line. So if you are to consider that, you're going to see that this is directly 90 degrees, this side, 90 degrees, that side. So instead of focusing with the 180 of a straight line, let us consider with the whole of the 90 degrees like this angle that we have. Okay, let me use this one. I want us to properly see this one. If you take this angle straight like this, going this side, this angle is 90 degrees. But out of the 90 degrees, we have removed this one, which is our alpha, this one, our alpha. So we are going to subtract 90 minus alpha, which is 90 degrees, minus our alpha, which is 5,711 degrees. Meaning to say, you remain with this angle inside of this one. This is the angle that you're going to remain with, this one, which is a combination of two angles, a combination of this angle and this angle. And this angle, because it's drawn from the center to this point, it bisects this angle into two equal parts. We talked about that. So meaning to say, to find one of these angles, we are going to divide by 2 because it is being divided or bisected into two equal parts. So that's the idea then. So this is going to give us 42,145 degrees. So the angle that is inside of the triangle, this one, the angle here inside, the angle here inside is going to be 42,145. This is the angle that you need in your calculations, this one. So let me just put it, okay, here. As are we going to see here? Or let me just put it here, 42,145 degrees. Let's hope you're going to understand me in that part. All right. So that is what is important it's important for you to have that. So meaning to say this distance, we do not know it. We're just going to call maybe this point E. So we're going to talk about from A to E and the radius. So AE, we're going to calculate it from this point. All right. Then we move from this point up to this point, from A up to A, which is our diameter, is involved. Then from this point A up to this point, it is the same as A to E. So I'm just going to call this point A, which is the same thing as what we had. So this one is already the same as what we had here. You can also calculate it from this side. Then from E up to the last point here, as you can see, this distance is the same as the radius. So meaning to say, at the end, we have got what? We have got a radius at the end. So that's what we have. So if we take a closer look, we are going to see that X is a combination of all these three. I mean, of all these along the horizontal line, we are going to see that X comprises of what? It comprises of R, which is the radius from this point up to E, which is the radius, plus from the point E to A, so I'm just gonna write it as AE, all right, plus from the point A to the point A, this one, A to A, like this one, which is what? Which is the diameter there, plus from point A to E, which is the same as AE on that side. This one is the same thing, so I'm just going to use the same AE. Then from this point E up to the end, which is the radius, which is the same thing as this one, which is our radius. So we have got the radius there. So it means we can calculate X because we have got the radius. Remember, we are given the diameter in this case. What is the diameter? The diameter is 18 millimeters. So if the diameter is 18 millimeters, radius is half of the diameter, all right? So we have the radius in that case. Let us see. All right, so the radius, which is the diameter over 2, remember our diameter was given as 18 millimeters from the diagram. So it's 18 millimeters over 2, which is going to be 9 millimeters. Not the diameter, this one. No, it's a different. We talk about the radius or from the rollers that we have. The radius, this one that we talk about, we are given it as 18 millimeters rollers. So we need the diameter of the radius of the roller. This one is the radius of the roller. This one is the radius that we have at the bottom side of the rollers. This one, all right? This is different. It's a different thing at all. So this is meaning to say here everything is there, except for AE, this one. The AE is the same that we talk about, but we do not have that. All right, so let us just simplify also X. We can just add R plus R is 2R plus AE, which is 2AE plus the diameter. So that means we need to calculate AE. So that's your mechano, guys. You have to calculate this, you form a formula. From that formula, you use it to calculate another part. That's your mechano. You just have to follow steps. If you know this, then everything is going to be much, much easier there. So to calculate AE, we are going to see something here, whether either side that you're going to use, either you're working with this side or the other one, you're going to see that you're formulating a right angle triangle, like I explained from the concept of a tangent meeting a radius. So you're formulating a right angle triangle. And I said these two angles will be equal. So that's where we got the angle of what? Of 42,143 degrees. Remember when we divided, this is at 90 degrees, and this is the radius from here to here is the radius. And remember, the radius of the roller is 9 from 18. We divided by 2, so we've got 9 millimeters. This is where our point A and where our point E is. So we can calculate this length. From our trigonometrical ratios, we have got the opposite and also the adjacent. That's the ratio of tan can be used from our SOHCAHTOA concept. So the tan of the angle of 42,143 is equal to, is it one? Oh, this is 145, not 143. So that's the opposite, which is 9, over the adjacent, which is AE. So in this case, we can calculate AE if we cross multiply. That is going to be AE times the tan of 42.145 degrees, which is equal to 1 times 9, which is 9. So to find AE, we're simply going to divide by the tan. So this is going to be tan 42.145 degrees, both sides by tan 42,145 degrees. So this was going to give us the length of AE. All right, so that's the length of AE in this case, which is going to be something like 9,945 millimeters if you round off to 3 decimal places. So with the AE that we have calculated, that means now we can be able to calculate X. Remember, that was the only missing part that we have on our formula. Everything is there, the radius, the diameter there from the bottom part. So therefore, our X was going to be 2 times the radius, which is 9 millimeters, plus 2 times AE. We calculated our AE, which is 9, so we got 9,945 millimeters, then plus the diameter, which is the diameter at the bottom here. Remember, our diameter at the bottom is 34 millimeters. So we are going to add the 34 millimeters. So that's it. We're going to have X, which was going to give us 71.89 millimeters at the end. So you must be careful on your presentation, what you're given, the information that you're given, how can you use that information to calculate whatever that you are given there. So this is our X from here to this point, it's 71. Let's just indicate on our diagram, 71,89 millimeters. So we now have X. Remember, the question is you're supposed to find X and Y at the same time. So X, we are done. Now we can find Y. 15 marks, guys. As you can see, there's a lot there that you need to consider. So let us try to find Y in this case. All right. So I don't think you're going to need this. Let us just remove this part. So let's consider this, guys. How can we calculate Y from the information that you're given? One, we need to locate where Y is situated. That's the first thing. Where is this Y that we're talking about is situated? This is the top part of the rollers here, the distance that we have between distance across the Y. So that means there is a lot to be taken there. There is a lot to be taken there. I want us to see something here. Y, it's a combination of a lot of things. If you take this Y here, I need this part BC. Yes, I think I'm gonna need this. Remember, we talked about this part before, so you're gonna need this part. All right. So anyways, if we check where Y is located here, we are going to see that it is a comparison of a combination actually of from this point here. If we check from this point up to the end here, there is a distance 1 in between here. Let me just save it like this. If we take it straight like this at the center, we take it straight to the center. From the center, it's only that my diagram is a little bit like shrinked when we have this. So if you are to consider this, you're going to see that this distance is representing the radius from the circle to the center. So this is the part of the radius. So Y is, it also consists of the radius. So there's a radius there, plus. Then there's a distance considered from this point here up to this point, which we do not know. Can we call, what can we call it? Because it's not a radius there. That distance that you're seeing, that piece, this piece that you're seeing there, it's not a radius, this one that is remaining here. So you can just maybe call it Y. So there's a distance Y that we need to calculate there. Then from there, we move from this point to this point. All right. And this point to this point and this point, which is the combination of the 50 at once. This one is involved because you are going to take BC, you take this point, you take BC together. What do they give you this? What are they going to give us? They are going to give us 50. So instead of taking one, we're just going to take 50 at once. So this is plus 50. All right. Then again, at the end point of 50, we're going to consider again, just like the previous case, that distance here from this point to this point, we're going to have our Y and also the radius. So you're just going to have Y plus the radius. So I'm going to talk about this Y here, but let us finalize our formula. So Y is equal to radius plus radius, which is 2R plus that smaller distance that we just called Y plus the 50. So the radius is there. Remember, from 18, you're just going to divide by 2, but we do not have this Y. So where are we going to have this Y? This piece that is remaining here. All right, let us consider this. This is the piece that I'm saying here, if you consider it properly here. All right, sorry, guys. I don't know why this board is now slow. If select something, it does not select at that moment. This is the distance that I'm talking about here, this space here that is remaining here, this space there, this space. You can just blockade that, you're done. So to have this space that we are seeing there, it is following that. It is actually, okay, let's consider this. Let's consider this. From this point here, from this point up to this point is the radius, this one. It is your radius, which is the same as this distance. If I take it up at this point, straight up to this point here, straight up, like this, straight up, you're going to see that this one is the same. This is the same radius. That my graph, my line is just shrinked. But this is the radius here. It's the radius, which is the same as from this point also up to this point. It is the radius. But if you take note now, this, it consists, the y that we, remember 50 ends here, guys. This is where 50 ends here, 50. This is where 50 ends. The y that we're talking about is this one, the space between here, this one. The y that we are talking about is this one, in between here. So this y that we are talking about, it is a combination of two things. It is a combination of this distance from this point up to this point, this one. It is a combination of this distance here from this point up to this point. If we add this point, this distance, and y together, we obtain the radius. So meaning to say the radius is the sum of this distance and y. So what are we going to call this distance? Because we do not even know this distance. We do not have even as this distance. So I'm just going to call this distance x. Do I have x? No, I don't have x. So I'm just going to let this smaller distance here to be x, like this. I'm just going to call this smaller distance here to be x. So it means y is a combination of two things. Now I'm not able to remove everything here. All right, let me just try. I'm just going to try to remove this part here. All right. Sorry for that, guys. Sorry for this. All right. So if you are to consider this, you're going to see that y is a combination of two things. The radius there, it gives us these two, the x, the smaller part, and the y, like that. So meaning to say, to calculate y, I must have this x, because y is going to be r minus x. R minus x is equal to y, and y is the one that we need on the formula. So y is equal to r minus x, where x is this piece, this one, this is x, this one. As we can see, we are formulating a right angle triangle there, like this. So on that part alone, this one, we are going to see that we are formulating a right angle triangle from that point of the circle going up like this, from this point of the circle here, going up this one, going up to this point like this, going like this. We are formulating a right angle triangle. I want you to see something like this. We are formulating something like this and joined like this. This is the part of x, this one, where x is. At the center, this is where our center is. I mean, the circle, like, this is where it is. So the question is, how can we calculate that smaller distance, this one? Because if we can have this smaller distance, we are done. All right, so if we consider this, we are going to see that this is a right angle triangle, and this is our x. The y is remaining. The y is this one. In air, we do not have, we do not have a shape that we form. But if we add these two, they give us the radius. So how can we calculate x? This is a right angle triangle. So we need this angle inside of the triangle. And also the length, n of this length. So in terms of the length, remember the whole of this length is what? Is 80. From here up to here, the whole of this is 80. Take note. From here up to that point is 80. And also from this point, you're supposed to be careful now. There you are supposed to be careful on this remaining distance, because this is 80, this one. From this point up to this point, it's 80. Then 50 is the center distance. From here to here, it's 50. So 80 minus, this 55. So if you check, there is a part that is remaining there down here. You have to take this one that is remaining down here, which is the radius of the roller there. And the radius is 18 divided by 2. So meaning to say there is 9 millimeters of the radius remaining. So to find this distance that we have here, because we are talking about from here, let me present it this way. We have from this point, from the ground up to this point. This is what we now have, the whole of that distance that I'm indicating here, from the ground up to this one. It's 9 plus 55. So we are ending at this point around there. We are ending here. As we need this one, so you have to subtract 88 minus this so that we have this distance remaining, which is this one. So how are we going to have this distance? We're going to subtract 80, the whole of this distance that we have there, 80. So it is going to be 80 minus the whole of this line up to the ground level. So it is going to, we are going to take 55 and 9 together. We combine these together. So that was going to give us 16 millimeters. So this is the distance remaining from this point up to this point. We are remaining with what? 16 millimeters there. So this is 16 millimeters that we are remaining with. All right. Remember, we want to calculate x. So the problem is we do not also have the angle. So where are we going to have the angle? And what is that we can use? We are going to see that this angle here at this point here, the angle that I'm indicating, this one, this angle that we have, and this angle are the same. All right, these lines, they are parallel. They are not going to meet. The line, that one, this one is a vertical line. So they are not going to meet. So you're going to see that this angle and this angle, they are corresponding angles from the concept of parallel. They never meet. So this angle and this angle are corresponding. So if this is 5,711 degrees, it's going to be 5,711 degrees also. This is your angle, 5,711 degrees. There are so many ways of finding this angle, guys. So many ways, as long as you apply your geometry properly. That is what you're going to have. So that means we can be able to calculate x, this one. We are able to calculate x. By calculating x, we are calculating y because it's going to be r minus x. So let's calculate our x. So what are we going to use to find x? This is a right angle triangle that we are having here. So what it means is that we're going to consider opposite, adjacent. So that's the ratio of tan. The tan of theta 5,711 is equal to the opposite, which is x, over the adjacent, which is 16. So that means we can calculate x. 1 times x, if you cross multiply, is equal to 16 times the tan of 5,711 degrees. So this was going to give us x, which is 1,6 millimeters. So that's we've got x. So by having x, that means we can calculate y, which is the radius minus x. And the radius, because it's a combination of the radius from this point up to this point. And the radius of the ruler is 8. Remember, the diameter is given as what? 18. So that is going to be the radius 9 minus the x that we calculated, which is 1,6. So that was going to give us y in this case, which is 7,4 millimeters. With the y that we calculated, we are done. We can calculate this y of the not this one is the small letter that we are using on this one, but this y on the top part is this one from this formula here. Remember our formula. Where did I write that formula, guys? All right, you see, guys, this thing of writing a lot of things. Now I can't remember where I wrote this. I think it was this side here. All right, so this is it. So therefore, y is equal to 2 times the radius. Remember, the radius from 18 is divided by 2, which is 9, plus 2 times y. We calculated the value of y in this case, and y was what? 7,4. So this is 7,4 plus 50. That's what you're going to have there. So this is what you're going to have. And that was going to give us 82,8 millimeters. So as you can see, guys, it was actually worth the 15 marks. There is a lot there that you need to consider. But if you're now used to these calculations, like you are revising a lot of questions, you see that it's just a repetition now. They are just repeating same information. So be careful on how you take your information and how you use the formulas in whatever that you are answering. Everything, you are supposed to be very, very careful in your presentations. All right, then the other part that we are given there, it was we had an epicyclic gear system, which is a gear train is shown in Fig 2 below. So this is what we are given here. Consists of the annulus, having 60 teeth, the sun gear that is connected to the output shaft, having 16, and so forth and so forth. All right, so this is what we have on our presentation. So we're just gonna consider this. All right, so remember, this one is just a repetition also. We say this is the annulus. All right, so you have to consider this part. The annulus in this case, which is the same as the outer part on this diagram, that will be your annulus. Then we have got the sun gear. In this case, we consider our sun gear at B, which is the same thing. We also have to consider the planetary, which is at D. This one, the part of the planetary D is our planetary. All right. So this is the major part that we are supposed to actually think of. And also we have got gear C, which is incline. This one is just an incline gear, which is at gear D, meaning to say these are at the same speed. So this one is an inline gear, not an inline. So guys, you see the way I'm doing now, an inline gear, which is at the same speed with the D, which is our planetary in that case. All right. So considering the information that we are given in this case, we are going to see that from this information we are given, all this. All right, let us just try and have our information aside. So this is what we are given. All right, A is having 60 teeth. So that is for A, the annulus is 60 teeth. Then B is connected to the output shaft having 16 teeth, B, 16, which is TB. That's 16 teeth there. Okay. What else? Then and rotates at 120. So B rotates at 120 clockwise. So clockwise is a positive. So NB is 120 revs per minute, which is a positive there. It's clockwise. Then what else do we have? Okay, let's just consider this positive here. What else are we given? We are also given that a planetary gear having 20 teeth and gear C having is mounted on the same axis. So the planetary gear, which is having 20 teeth. So this is for TD, the planetary, which is 20 teeth, which is in line with gear C. They are connected together, and gear C having what? 24 teeth. On the same axis. 3.1, if A is fixed, if arm E is fixed, calculate the speed and direction of the annulus A, and also determine the speed and rotation of arm E, assuming that the annulus is fixed. All right. So this one, there are two questions, but what you're going to do is to answer this on a single part. So remember, what is happening here is that we are simply considering the idea of our driver-driven concept. That part is not going to change. So the annulus, which is A, it drives the planetary. Remember, we talked about that. So A, which is our annulus in this case, which is A, is going to drive the planetary, which is D. So it drives D. Drives D, which is the planetary, in the same direction. So if it is driven in the same direction, so it's going to be T, the number of teeth of the driver over the number of the driven, which is TD. So that's what you're going to have in the same direction, driver over driven. So it's going to be driver over driven there. But D and C are in line. They're at the same axis. So they're at the same speed. So D and C, this is what you need to know. D and C are mounted on the same axis. Are mounted on the same axis. So if they are mounted on the same axis, what does it mean? It means that we are going to have the same speed as of D and C. So meaning to say the speed of C is equal to also the speed of D. That's what you're going to need. All right. Then let's move on to the other part at C. C is now driving B. So C drives B. So C drives B. All right. So, but now what is going to happen is that this, as it is moving in the clockwise, B will be anti-clockwise. So it's going to be driven in the opposite direction. So C, it drives B in the opposite direction. That's what you need to know, in the opposite direction. But at the end, remember, it was a combination of three. It was a combination of the speed at D, the speed at A that we have to consider there in our calculations. So this is very, very important to be taken. So remember, these two, they work together. So in order for us to know about the speed that we're going to have, it's going to be the driver over the driven, T drive over T driven. We're going to talk about those formulas, the product that you're going to have in the opposite direction. But as you can see, it's a combination that is going to be affecting these two. All right. So meaning to say you are supposed to be very, very careful before you attempt anything. Do you understand this information on our presentation? All right. So like we are told to determine these speeds, we're going to need our table, the table that is going to show us how this information is to be related. So I'm just going to have this table on this side so that you can see how to use it. All right, so with something of this, we can fill in our information in that case. So you're just gonna have the number, remember, gonna just have your conditions. Let us consider, so we are supposed to start with the annulus in this case, and what is affecting the annulus, which is the outer part in this case, is our gear A, remember? All right, I inserted another page. Let me just do this. So remember, the annulus is our gear A in this case. So you're supposed to have this as gear A, which is our annulus. So we are supposed to have our annulus, which is gear A, to the planetary in that case, all right, to the planetary. And our planetary is gear D, according to this information, our planetary, which is our gear D. So meaning to say, you're gonna have gear D in this case. From the planetary, we said gear D and gear C, they are inline. So you're going to include the inline gear in that case, all right? And your inline gear, which is gear C. Then from there, you move on to the sun gear. So this is how the movement that you have on the deck is the same that you must have there. So it's going to be easier for you. The sun gear, which is our gear, that was our gear B, according to our information there. The sun gear is our gear B. If you know this, the same way that we had there from A to up to the last one in that movement. That is the case. And lastly, the arm is to be considered. And that case, we consider the arm, and the arm is referred as what? The arm E. That is the case. The annulus to the planetary. If there is an inline gear, the inline gear, then the sun gear. All right. So our conditions, they are not going to change whether it has got, or there is no this part, or this part is there, or the condition, the first one is not going to change. The first condition that you're going to work with is to fix the arm, and you rotate the annulus. You fix the arm and you rotate the annulus. So fix the arm and you rotate the annulus. So in this case, our annulus is gear A. So that's why we have to write gear A. But what you are doing there is you are rotating the annulus plus 1 revolution. So that is, guys, look where I'm writing now. I'm writing where I'm not supposed to be. I wanted to have it this way. It's this thing of having, I'm not supposed to even write this number here. All right, so we said just gonna fix the annulus, annulus, which is gear A, all right. Fix the arm, guys. You see now, this thing of erasing and this, that. You fix the arm there, then you rotate the annulus. Rotate the annulus, which is gear A. All right, +1 revolution. So that's what you're going to have there. It's a fixed condition on each and every part that you're going to have. I have you guys asking, is it like you're supposed to have this every time? Yes, you're supposed to have it in each and every condition. That one is a fixed condition that you're supposed to have. You fix the arm, you rotate the annulus. So meaning to say the annulus will be standing at +1 revolution. So D is affected by the annulus. That's where now we go back to that information that way, that A drives what? A drives D. So if A is driving D, the annulus driving what? D, which is our planetary. Therefore, the speed there is going to be given as TA over TD, driver over the driven. So meaning to say the speed here is going to be given as TA over TD. If you understand that, it's not going to be a problem. So this is TA over TD. So that was our TA from the diagram, TD. Also, we have these values for the number of teeth, TA, the teeth on A, which is 60, and that of D, which is 20. So 60 over 20 there. And they are rotating in the same direction, so it's going to be a positive. All right, that's it. What about gear C? Gear C is an inline gear, so it has the speed as what we have at D. Remember, we talked about this. D and C are mounted on the same axis, so the speed at D is that the same as what we have at D. So meaning to say even here, you're just going to have 3. And the sun gear now is a combination that is, we're going to have the product of A and C. Remember, C is going to drive B. So you're going to have the product of the drivers over driven. So the drivers in this case, considering on our diagram, remember the drivers, it's we said is the annulus A driving D. So that is the driver. We are considering A, the drivers over the driven. So the driver, we have got A, so it is going to be TA. Then the other driver that we're going to consider is C. C drives what? C drives B, so it's going to be times TC, the product of the driver over the driven. A was driving what? A was driving D, so it's going to be TD times C is driving what? C is driving B. So this is the formula that you're going to use, but remembering that I said C drives B in an opposite direction, so it's going to be a negative. It is in the opposite direction. So meaning to say this is the formula that you're going to simply use there. So you can even separate as TA over TD times TC over minus TB. That's how you can even have this formula written in the formula sheet, but that is what they are trying to say there. That is what they are trying to present. So you saw is the product of the drivers on top. So that is TA over TD multiplied to another driver, C driving. C is going to be driving what? Driving B. So it's TC minus over minus TB, driven in the negative direction. So TA over TD, TA over TD is the one that we already have, which is 60, or the 3 that we calculated before. So you're going to need TC over minus TB. TC, what do we have for TC? Number of teeth there at C. At C is 24. That's our TC. Then our TB is 16. So it's going to be 24 over minus 16. So this will be 24 over negative 16. So that's it. We are going to have negative 4,5. So this is negative 4,5. Then what about the arm? Remember, the arm is the one that is being fixed. They fix the arm. So meaning you say there's no movement for the arm, it will be at 0. Guys, that is all. That is all neat. Just like that. Everything there now is just something, a follow-up. As long as you're done with this part, the first stage, you are done. So what are we going to do on the second part? On the second part, we are simply going to multiply by X and we add Y on each and every part. So this is what we are going to have. So you multiply each part there, you're going to multiply by X. Then after that, you add Y and add Y. So this one, you multiply it by X, 1 times X, which is X, whatever that we get, we add Y. 3 times X, which is 3X, whatever that we get, we add Y. 3 times X, which is 3X, whatever that we get, we add Y. Minus 4,5 times X is minus 4,5X, whatever that we get, we add Y. 0 times X, that's 0X, which is 0, whatever that we get, we add Y. So it's just going to be a Y. Just like that. You're multiplying everything, this by X, get whatever that you get, you add Y, this by X, whatever that you get, you add Y, and so on and so on. So now the questions that you are given, like I said before, that the questions are the ones that you are now answering. This part that we are going to fill in here, it is the part that is from our question. What is the condition that you are given from the questions that we have? There are 2 questions that we are given. From one table, we are answering 2 questions that we are having there. What am I trying to say? From one question, all right, let us consider the first one. There are 2 conditions that we are given there. The question was, in this case, all right, let us go back to our question. They are saying the 3.1. So these are the questions now that you're having here. The first question, it was, if E is fixed, calculate the speed and direction of the annulus if E is fixed. So that's our 3.1. So 3.1, to calculate the question on 3.1, E is being fixed. That is what we have. That's the condition of 3.1. E is fixed, meaning to say E, we do not have the speed. It is fixed. So its speed is at 0 revs per minute. There's no movement. It's fixed. If E is fixed, calculate the speed of the annulus. What is representing the annulus? The annulus is A. So the question is asking you to calculate the speed of A. That is the question. That is one only part that you have. But if you check, there's a speed that we are given, and that is not going to change according to this information on our diagram. This one is a fixed part, which is the speed at B, which is 120, which is, in this case, considering the sun gear D. We have the speed there of 120. So this one, it's fixed and it's clockwise. So meaning to say, we are going to work with that speed also of our sun gear, which is B. So in this case, we have got its speed of the sun gear, which is B. So the speed of B is given as a positive, meaning it says an clockwise, which is 120 revs per minute. This is the information that we have from 3.1. We use this information to calculate NA. So meaning to say, we do not have, or we do not know this, the speed of gear A. We do not have this. We do not know this one. So NA, we do not know this. But at D, is there anything? No, there's nothing. At C, there's nothing. At B, that's where we have that fixed of 120 in the positive. And remember, they said the arm is fixed. So there's no speed there of the arm. With this information, we can calculate the speed of A. That's our question 3.1. Question 3.2 is the one following with its own information. That's question 3.2 now. And what is the information about question 3.2? 3.2, they are saying determine this time the speed and the direction of the arm. So we need the speed of E. Assume that the annulus is fixed. This time, it is the annulus which is fixed. And you need the speed of what? The arm, which is E. So what is going to be the speed of the arm, which is E? We do not know the speed of the arm, which is E. But provided the annulus is fixed, remember the annulus is A. So if it is fixed, it means there is no movement. It's 0 there. It's fixed. There's no movement. Just like what we had before. The annulus was the one that was fixed. So this is what you're given. But remember, B does not change. With this speed, our B was at positive 120 revs per minute. So with this information, we can calculate the speed of the arm, which means we can calculate, right, the gear A, which is the annulus. If you consider the annulus, that is the one that is being fixed. So that's a 0 there. We do not have anything about this part of our gear D and gear C. So this part, just gonna leave it like that. Then you move on to the other part, which is gear D, the sun gear, which is the one that is at 120. We are given that one. So this is the one at 120. They want us to calculate NE, which is the speed at what? The speed at E. So that is the question there. So question, the question 3.1, you answer it from the information corresponding to that part, which is this one. This is the information which answers question 3.1. This is the information which answers question 3.2. So you have to be careful. All right. So 3.1, we wanted to calculate the speed at A, which is the speed that is affecting the annulus if the arm is fixed. So what you're going to do is to simply equate these equations to question to your question. So let us answer question 3.1. So you simply equate x plus y is equal to NA. These two are equal. So it's an equation that you're formulating there. X plus y is equal to the speed at A. Then here there's nothing to formulate. All right, here there's something, minus 4,5 plus y is 120. So minus 4,5 plus minus 4,5x plus y is equal to what? 120. And also y is equal to what? Y is equal to 0 from that other part, y is equal to 0. So if y is equal to 0, it means, what does it mean? If y is equal to 0, it means x is equal to NA. So by calculating x, we are calculating the speed of what? We are calculating the speed of, what? Of A, which is the annulus in that case. All right, y is a 0 there, so I can take advantage of the second equation because I'll be just left with minus 4,5x being equal to 120. It's a straightforward equation that I'm having there that I can use to calculate x. If I divide by minus 4,5 both sides, I can have the value of x. 120 divided by this minus 4,5, we are going to obtain negative 26,667 revs. Okay, this is just x for now. Then, like I said, that's a 0 there. So therefore, x is equal to NA, or NA is equal to x, which is the speed of the annulus. So our x was what? Negative 26,667. Once is the speed, therefore you're gonna have this in revs per minute. So the negative simply means that there's an anti-clockwise direction that we're talking about. That is why we're having what? The negative speed. So this is what 3.1. So use the information for 3.1 on the table. It's no longer applicable that you calculated this. This one is no longer applicable because it was a conditional question. It was calculated out of a condition. 3.2 is another condition to be considered. So you can't use a condition that you calculate that to calculate that one for 3.2. It's on its own. So what is the condition of 3.2? This is our 3.2 now. On 3.2, this is what we have. These are the conditions. So this time we equate these to the 3.2. So we are now answering question 3.2. So on 3.2, we need to calculate the speed of what? The speed of the arm. That is the one that we need there. But taking that x plus y is what? As 0 there. If we equate this, they're saying from our diagram, x plus y is a 0. Also here, you equate this minus 4,5 minus 4,5x plus y is equal to 120. And what we need in this case is NE, which is the speed, and y is equal to NE, which is the speed of the arm. So it states that y is equal to NE, which is the speed of the arm. So by calculating y, we have calculated the speed of the arm. So how can we calculate y? That is the question now. So due to your manipulations, guys, you can just manipulate, make x the subject, then I substitute somewhere so that I just remain with y because I want to have y. So you can just have my equation in favor of y because y is equal to NE. So just calculate y there. So you're going to calculate y because that's what we want here. So from equation 1, this is my equation 1, this is my equation 2. I can take advantage of any equation. All right, so let me make y the subject from equation 1. From equation 1, I'm going to make x the subject, So if I make x the subject from equation 1, it means x is equal to minus y. X is equal to minus y. So what I'm going to do is to substitute this one, x is equal to minus y that we had from equation 1 into equation 2. So you're going to substitute this into equation 2. You substitute into the other equation. So in place of x, we are going to substitute minus y. That means we've got minus 4 comma x times x. Our x is minus y plus y. This is equal to 120. So minus 4 comma 5 times positive y is going to be 4 comma 5y plus y is equal to 120. And that we can calculate the value of y. So this is a positive there. So if we add 4 comma 5 plus 1 is going to be 5 comma 5 y, which is equal to 120. If we divide by 5 comma 5 both sides, that's we have the value of y in that case. So this was going to give us the value of y. Why concentrating on the value of y? Because NE is equal to y. So there's no need for me to calculate x. Yes, I can do that, but guys, consider to say the question is y is equal to NE. So we can just calculate y straightforward instead of calculating x. Then after that, all right. So that's our NE. And NE is equal to y. So therefore, our NE, the speed of the arm E is going to be equal to y, which is 21, so this is 21,818. Once its speed is now revolutions per minute and being positive, it means we are taking this in the what? In the clockwise. That's a positive. If you're having that, it means positive in the what? In the clockwise. So you see how these questions can be given. They want you to be very, very careful how you relate, but your table is not going to change the information if you take the way that I'm trying to present here from the conditions. This way, if you take it this way, the annulus, the planetary, the inline gear, if there is an inline gear to the sun gear up to the arm. The conditions, the annulus driving the planetary and the inline gear are together, and the inline gear, it drives the sun gear in the opposite direction. Simple, like that. You can answer any question with this information. So also, we are going to have introductions, guys. I'm coming there. It's only that you remember the issue of time, this and that. But we're going to have also introductions, like talking about the gear drives. We just said questions, this and that. But other topics, I think we can see they are already in progress. Like other areas of our syllabus, they are already in progress with our introductions. So make sure that you watch them so that you understand more on these areas, because as we are doing questions like this, I'll be expecting that there's an idea that you know about that area or about that topic that we'll be discussing. So you ought to also just have to work with more and more and more and more question papers as you can. All right, so that's it, guys. We have to work more question papers. Actually, we're going to consider question number 4. So number 4, it was a belt drive that we are supposed to consider there. And they are saying it's a belt drive consists of 3 V-belts. So that's a V-belt that we are considering in this case. So you've got the number of V-belts, which is the number of V-belts, N is equal to 3. On a grooved pulleys, on a grooved pulley off, so that's a grooved pulley there, of 40 degrees. So remember, if it is a V groove, you're going to need the half groove angle called alpha. Alpha, the half groove angle, which is 40 degrees over 2. So you have to divide this by 2, and that will be 20 degrees. So this is your half groove angle. We talked about this angle. This one is our half groove angle. So the area, the cross-sectional area of each belt is 300 square millimeters there. We are given the area. Let us just write this. We do not know. Maybe you're going to need to change it or to convert it later on. But we're given the area of each belt as 300 square millimeters. And the maximum tensile stress induced in the belt may not exceed 7 megapascal. So we are given the maximum stress that is our maximum stress is not supposed to exceed this. So it means the maximum stress is 7 megapascal. The coefficient of friction between the pulley and the belt is 0.2. So we also have the coefficient of friction 0.2 between the belt. That is what you're given there, and the pulley, which is 0.2. Each belt is 400 millimeters in diameter and rotates at, so the diameter is 400 millimeters, which is actually 0.4 meters, and rotates at the speed, which is 300 revolutions per minute. So they rotate at 300 revolutions per minute. So with this information, the question was to calculate the power that can be transmitted by each belt if the contact angle between the pulley and the belt is 180 degrees. So the contact angle, that is our theta. So theta must be in radians, our contact angle. So remember, 180 degrees, guys, is 2 pi radians. We know that is equivalent to 2 pi radians. 180, it's pi. 360 is 2 pi. Guys, you see now this way. So 180 degrees is pi radians, all right? Then if it is 360 degrees, is what? Is 2 pi. So we need to calculate power from this information that you're given here. Remember I said when you are dealing with this condition of a V-belt from the other calculations that we had, that the power is going to be given as the effective tension times the velocity times the number of the V-belts. You have to consider the number of V-belts there, whereby this is the effective tension, the difference between T1 and T2, which is the tight side and the slack side. Then we also need the velocity in meters per second. We do not have also this one. So there's a lot of things that we do not have there. All right, so let us consider these separately. We're just going to try and calculate these ones. From the maximum tension that we are given, it follows that we can calculate the tension on the tight side. The tight side is the one that uses the maximum tension. Remember, guys, this is the tight side. So it follows that the tension that we have on the tight side is the maximum stress times the area. So that is what you're going to have. So that is our maximum stress is given as 7 megapascal. That is 7 times 10 to the exponent of 6 times the area. There, the area of the belt is given as 300 square millimeters, and this must be in square meters. So to convert to square meters, we multiply by 10 to the exponent of -6. So this will be 300 times 10 to the exponent of -6. From square millimeters to square meters, all right? From square centimeters to square meters, you multiply by 10 to the exponent of -4. Your answer will be in square meters. So you have to be careful on the units conversion. So this was going to give us 2,100 Newton. That is, we've got the tension of the tight side, which is T1. So to find T2, let us consider, because we need T2 also. So to find T2, remember, we have got the ratio of tensions, the ratio between T1 and T2. Remember, our ratio, we do not have the mass, so the centrifugal force is not to be considered. So we are going to use this formula. Remember, for a V-belt, T1 over T2, the ratio is equal to e to the exponent of micro theta. Then we're going to have cosec. There's the groove angle. So you're going to include cosec alpha for the groove angle there. Remember your formulas, guys, where cosec is 1 over the sine. So that means we can have T2 if we cross multiply and divide by this. It follows that T2 is going to be given as T1 over the whole of this part, which is e to the exponent of micro theta, the cosec of alpha. So that's it. We can calculate our T2 in this case. So T2 is going to be given as T1. We calculated T1, which is the maximum, which is the tension from the tight side from the maximum stress that we're given. We got 2,100. So this is 2,100 Newton over e to the exponent of the coefficient of friction, which is, that was 0.2. Is that so? 0.2. So we've got 0.2 times theta in this case, which is our contact angle in radians. So our contact angle, which is pi, remember 180 degrees, we say this is equivalent to what? To pi. Then times the cosec. This one is in degrees. Alpha is in degrees, and cosec, it's 1 over sine. So it's going to be 1 over sine our alpha, which is the half groove angle, which is 20 degrees. So you use the half groove angle there, that is 20 degrees. So this is what you're going to have in your calculation. So when you're calculating, your calculator now is in degrees here. Your calculator is in degrees, all right? So you're going to obtain T2 in this manner. We are going to obtain our T2, or we can simplify this, but it was going to be something like 334,501 in Newton. So this being our T2, we are going to use it now to find TA, which is the effective tension, because we saw that on this formula, we are going to need the effective tension. Guys, it's just 5 marks, but a lot of calculation, and I don't know why do they limit marks on this one. But anyways, that is what you're going to need there. So our effective tension is the difference between T1 and T2, as we know, guys. That's our effective tension. T1 from the tight side, that is 2,100. So we've got 2,100 minus T2, 334,501. That is our effective tension at the end. And that was going to give us 1,765,499. All right, so that will be 499 in Newton. So this is your effective tension, the one that you're going to use on those calculations to find the power, as we saw that we need the effective tension. We do not have the velocity, so we are going to need the velocity. All right, the velocity is given by what? All right, so remember we've got the diameter there. We do not have the thickness. All right, so let me just erase this part. I don't think we're gonna need this. All right, since we have calculated our effective tension, let me just remove this part. So remember, if you are given the thickness, if there is a belt thickness is involved, it follows that the speed is going to be taken as, which is our V, is going to be pi into the diameter plus the thickness times the speed, which is in revolutions per second. You can convert this to revs per second, but we do not have the thickness. So meaning to say we are going to use pi dn. So it's just going to be pi dn over 60, so that we have this in meters per second. Since our speed is in revolutions per minute, we have to divide by 60. So that's it. You're going to have your velocity there in meters per second. So that is pi times the diameter in meters. Our diameter in meters, that's 0.4 times the speed in revs per minute, which is 300. Then we're going to divide by 60. By dividing by this, we're going to have the velocity in meters per second. So the velocity there was just going to give us 2 pi. And 2 pi is same as 6,283 meters per second. So that's it. We have got the velocity, the effective tension, the number of V belts, which is 3. So therefore, the power can be calculated because power is the effective tension. And we calculated our effective tension here. Got 1,000 is that part that we had here. So we're going to use that on our calculation for power, which is 1,765,499 times the velocity of the belt. That is, we calculated the velocity of the belt in this case, which is 6,283, or you can use pi there, times the number of V belts, not the speed, but the V belts. This one, there are 3 V belts to be considered. So you multiply by the number of V belts, you are going to obtain the power in that case. And the power was going to be 33,277,891 in watts, which you can convert to kilowatts if you divide by 1,000. So that is going to give you 33.278 kilowatts. So this is the power that we are going to have at the end. So you have to be careful in your presentations. The information that you're given, all the stages that you're going to take, the formulations, this and that. Guys, that's it. Number 5, which is on hydraulics. So the first part, we were given that a pipe conveying water equipped with a Venturi meter with the following specifications. All right. So this we are having, or we are dealing with a condition where a Venturi meter is considered. All right. We had actually, did I had this introduction of the Venturi meter? But I think now for these ones, we have done like or everything on this part. All right. But anyways, it is having a Venturi meter, and we are given the diameter of the water pipe, the throat of the Venturi meter, the mercury reading of the manometer, and so forth. All right, I remember. Yes, I did the introduction of this one. So it is important that you do watch the introduction of this part so that at least you can have an understanding of what is happening on this part. All right. Well, you must have an understanding of what is happening. So the question was to calculate the delivery of the pipe. All right. So remember, on the Venturi meter, I was stating that you are going to have a condition at the inlet part. All right. You are going to have a condition at the inlet. Then it goes to the throat where you are having now the outlet part. Right, guys, you see me as the issue of the drawing as my disadvantage when it comes to the drawing part. You see, guys, I have a problem. So that's why I further my explanations for you to understand, because my drawings, they are something else. But we had something like this. All right, then it goes to the exit there. So at the inlet, we're gonna have the diameter there. Then we're gonna have the part of our throat in this case. All right, so just gonna have something like this. All right, but if you watch the video on the introduction, I hope this can make sense. That can actually make sense. So the meter entrance is this side of the entrance. So this is our 0.1 and our 0.2, which is at the throat. At the throat. All right, so that is what you're given. Like, okay, guys, like I said, just make sure that you watch the introduction. All right, so they were given the diameter of the water pipe, not the water pipes, but that the pipe that you're given, its diameter is given as 80 millimeters to meters. That's 0.08. If you divide by 1000, then the throat, which is D at the throat, in this case we are talking about the throat, the diameter 30 millimeters divided by 1000, 0.03 meters. Then the mercury reading manometer 25 millimeters. That is the height of the mercury. Remember, I said H1 for mercury. All right, so you're given H1 for mercury, which is in meters, 0.025 in meters. The coefficient of delivery, we also have the coefficient of delivery, which is 0.95. The coefficient of delivery does not have units. They're not supposed to write millimeters. It's just 0.95, does not have the units. All right. So this is what we have. And the question needs us to calculate the delivery of the pipeline in liters per hour. Take note, they want this also in liters per hour. The delivery that we are supposed to calculate, which is our Q from our formula, is supposed to be in cubic meters per second. That is what you're supposed to have. So there they need the delivery, not in cubic meters per second, but in liters per hour. So there are two things to be converted: cubic meters to liters, and also seconds to hours. But let's start by calculating this, the delivery. Remember, I said from our introduction, we can calculate this by using the formula. There are two formulas that I talked about there, that Q can be calculated when dealing with a Venturi meter. Q is equal to the coefficient of delivery times the area that we have at the inlet, times there's this square root that is called the square root of 2GH, the square root of 2GH over M squared minus 1, where M squared is equal to, remember I talked about this formula, where M squared is equal to D over D to the power of 4, which is simply taken from D to the power of 4 over D to the power of 4. We had this. Or we can use that other formula for Q. If you want, you can use that other one, where Q is equal to the coefficient of delivery times the area of the pipe times the area at the throat times the square root of 2GH like this, everything over the square root of area squared of the pipe minus area squared of the throat. So this still gives us the same thing. That is where we are going to have the flow rate in cubic meters per second if you use this formula. All right, so as for me, I'm going to opt this one. I'm going to opt this one, the second one. All right, so I want you to use the second one to prove, this one to prove and see if you're going to win. But as for me, I'm going to work with this one. Meaning to say here, I'm just going to need the area of the pipe, and I'm going to need m squared. Everything is there. And also, I'm going to need this H. This H is not for mercury, it's H for water. This is the delivery for water. So this H is the head of water. This one is for water. It is the head of water that you're talking about there. So we also need to calculate this. It is the same thing even here. You are going to calculate that same head of water. All right. So let's start with the area of the pipe from the diameter of the pipe at the inlet. That's where we have the diameter of the pipe. So meaning to say we can calculate this A. A is equal to pi d squared from the diameter of the pipe. So that is pi times the diameter of the pipe 0.08 squared over 4. So this is going to give us the area of the pipe in that case. And that was going to be 0.00503 square meters, something like that. This is what we were going to have at the end. All right. So this is what we're going to have at the end as our area. All right. So we've got the area of the pipe. So this is the area of the pipe. So if you were to use this formula, you were going to calculate the area at the throat. So the area at the throat, you use the diameter of the throat, which is 0.03, which is the diameter of what? Of the throat. All right, take note. But like I said, I'm going to use this formula. So on this formula also, I'm going to need m squared. And m squared, like I said, where m squared is d to the power of 4 over d to the power of 4, the diameter of the pipe to the diameter of the throat. All right, so let me just erase this formula because I'm not using this one. So I'm going to calculate also m squared in that case. And m squared is equal to, that is the diameter of the pipe to the diameter at the throat to the power of 4. So you're just going to write it like this, d over d to the power of 4. That's the easiest way that you can just have them. So meaning to say, just going to insert the diameter of the pipe, 0.08 to the diameter at the throat. The diameter at the throat is 0.03. So that was 0.03 there, 0.03, everything to the power of 4. So that was going to give us m squared. And m squared was going to be 50.568. So that's your m squared there. So you can actually work with this m squared. So these are the things that we need on our formula, m squared. We need the area of the pipe in this case. Also, we need the head of water. We are given the head of mercury, but on the formula, we need H for water. So remember, I told you guys on this that there's a relationship that between the head of water and that of mercury. The head of water is 12.6 times the head of mercury. So that's 12.6 times H mercury. That's the relationship between these two. All right. So meaning to say we're going to have 12.6 times the head of mercury, which is 0.025, which is the height of mercury. You've got the height of water if you do this. All right. So that was going to give us something like 0.315 in meters. So this is the head that you're going to use of water. That's the idea there. That's the idea. So everything that we need on our formula is there, the head of water, m squared, and also the area of the pipe. So with this, we can calculate the delivery in cubic meters per second. Take note of the units that you're going to have first. So the delivery from the coefficient of delivery, which is 0.95, times the area of the pipe. Remember, the area of the pipe we calculated 0.00503. So this is 0.00503 times the square root of, so if you're using this formula, you're going to have the square root of 2 times the gravitational acceleration of 9,81 times h, which is the head of water, and the head of water is 0,315. So this is over. We're going to divide everything to what? M squared. M squared, we calculated M squared is 50, this is your M squared. Don't square it already, it's M squared as it is. So this is 50,568 minus 1. So that is what you're going to have in that case. So with this, we are going to have the delivery in what? Cubic meters per second. So the delivery of water was going to be given, or we were going to obtain something like 0,00169 cubic meters per second. So these are the units that we are having. Remember, the unit conversion part is important because they need you to have your answer not in cubic meters per second, but in liters per hour. Liters per hour. All right, let's start with the cubic meters to liters. How do we convert the cubic meters to liters? Each cubic meter that we have is equivalent to 1,000 liters. That's what we have. So meaning to say, to convert this to liters, we're going to multiply by 1,000 because each cubic meter is 1,000 liters. So our delivery is going to be, if we multiply by 1,000, it's going to be 1, that will be 1, 2, 3. So it's going to be 1,690. Just use your calculator there. Liters per second. We are now in liters per second, but remember, we need liters per hour, Now we are in liters per second. So how do you convert per hour? 1 hour is equivalent to 3,600 seconds. A second is equivalent to 1 over 3,600 hours. So it's either you're going to divide by 1 over 3,600 or you just multiply by 3,600. So by multiplying by 3,600 seconds, we are automatically converting this per hour because we're going to have 1 per hour. So that means our Q is going to be liters per hour. This is now hour. So this was going to give us 6,084 liters per hour. So take note. So these values, because of rounding off this and that, that's at the end, you end up having affected values, but this is exactly what you need in your calculations. And that is what you're going to have at the end. So just make sure that you have all the presentation properly given, all your formulas and so forth. So that was it for the for this Orifice. In this case, if you're dealing with a Venturi meter, they can give us something like that on a Venturi meter. So make sure that you watch the introductions there. That can help you, and also to use the other formula I stated how to apply or to use the other formula in case that you want to use it. But that's it. All right, so let's check the other part, which is 5.2. 5.2, we are now given the condition of an orifice. So given this, an orifice, the diameter, this and that also, no, an orifice, we never talked about it, but that'll be the next part that we're going to talk about, an orifice, no problem. So anyways, we are given that they determine the coefficient of discharge of an orifice. All right, so we need the coefficient of delivery, given the diameter inside the tank containing water under the head of 4 meters, the actual discharge of water from the orifice is, so you're given the actual discharge and so forth. So there we need our formulas and manipulation. Yes, we just had, I think it was a question which was relating to that, but we're going to have this part of the constants working with with an orifice, flow of water through orifices. All right, so an orifice actually is just something that you're gonna have. This is 5.2. So you're gonna have a part of that the flow of water coming out of the orifice like that. All right, so in this case, you'll be having a lot of like the flow of water is going to be considered, and also the heights that you're gonna have, the difference in terms of the heights, in terms of the water that is inside of the tank, and also the pressure that you're going to have, this and that. All right, the constants, the coefficients that are needed, talking of the actual values, the theoretical values, this and that. All right. So what is important is that we're going to have it as an introduction, just like another part that we had. But in this case, I want us to check, okay, this diagram was for another person. I just thought maybe I had inserted this, but let us take our information and see. So we are given there the coefficient to determine the coefficient of discharge, which is the coefficient of delivery. So we do not know the coefficient of delivery of this, but given that the diameter is 60 millimeters inside, so you're going to divide this by 1000, and the height, which is the head, is what? It's 4 meters. So we've got two things there, the diameter of 0.06 in meters, and also the head of water, which is 4 meter inside. So these are the conditions that are being taken inside. Then also what we are given there is that the actual discharge of water from the orifice is 54,000 liters per hour. So the discharge is given in liters per hour, which is supposed to be given in cubic meters per second. So we have got the actual discharge or delivery, 54,000 liters per hour. So remember, we had a condition like this, and where we converted to liters per hour. So you have to convert back to cubic meters per second. 1 liter is 1000. 1 cubic meter is 1000. So you're going to divide by 1000 in this case to convert to cubic meters. So this will be 54 cubic meters per hour. 1 hour is 3,600 seconds. So meaning to say we're going to have 54 over 3,600 seconds to convert to cubic meters per second. So that's 54 over 3,600, which is going to give us something like 0.015 cubic meters per second. Remember, the delivery is supposed to be in a cubic meters per second. So we are given the actual delivery there. All right, that is the actual delivery, which is 0.015 cubic meters per second. So this is the information that we have there. Let us check what we can do. So the question was, from this information, calculate the coefficient of delivery. All right, it follows that the coefficient of delivery from our formulas is going to be taken from the actual. We're going to have the the ratio actually is the ratio of the actual flow, which is the actual flow to the theoretical flow. So in this case, we have got the actual flow is already given in this case. All right, this one is given, but we do not have the theoretical flow. So the theoretical flow is going to be taken from where? That is the question. So the theoretical flow is going to be taken from the theoretical velocity and the theoretical area. Take note, theoretical flow must be from the theoretical, this is from your coefficient. Remember, from those three coefficients, the coefficient of velocity, coefficient of contraction, coefficient of discharge. So it follows that QT, which is the theoretical flow, is equal to the theoretical area times the theoretical velocity, or theoretical velocity times what? Theoretical area in cubic meters per second, where we need the theoretical area and we also need the theoretical velocity. Remember, theoretical velocity can be taken from the square root of 2gh. All right, so this one, we have the formula for VT, the theoretical velocity, remember, is taken from the square root of 2gh in meters per second. So that means our theoretical velocity is going to be the square root of 2 times the gravitational acceleration of 9.81, then times the head, which is the height there of 4. So that means our theoretical velocity was going to give us something like 8.859 meters per second. So we have got VT, the one that we need on our calculations. Then we also need the theoretical area. The theoretical area is the one that is calculated from the diameter of the orifice. From the diameter of the orifice, take note, from the diameter of the orifice. So in this case, we're given the inside diameter of the orifice in this case, which is this 0, that is the inside the orifice. So meaning to say we can use this one. That is AT is given by this formula. Remember, AT is given, that is the theoretical diameter is going to be, theoretical area is going to be pi times d squared of the orifice, in this case, over 4. So you use the diameter of the orifice. For the actual area, you use the diameter that is the vena contractor. All right. So this is going to be pi times d of the orifice. Remember, our diameter was given there as 0.06. So it's 0.06 squared over 4. So this was going to give us the theoretical area of something like 0.00283 square meters. So having the theoretical area, it means we can be able to calculate the theoretical discharge, which is the one that we need here. So the theoretical discharge is calculated from which formula? Remember, our theoretical discharge that we are talking about is going to be theoretical area times the theoretical velocity. That is 0.00283 times the theoretical velocity that we had from this formula, 8.859. All right, so this is 8.859 like that. So that is going to give us the theoretical discharge. With this one, we are going to obtain the theoretical discharge, which was going to be 0.0251 cubic meters per second. So with the theoretical discharge, we are able to calculate CD, which is the coefficient of delivery, as what we are given on our question. So therefore, the coefficient of delivery was going to be given as, all right, so just going to remove this part here. So the coefficient of delivery, which is our CD in this case, was going to be the actual flow rate, which is the actual discharge, which is our actual discharge. It was 0.015 cubic meters per second over the theoretical discharge, which is this one that we got of 0.0251. So dividing this, we are going to obtain the coefficient of delivery or discharge of 0.598. All right, so that was our question there. That was our question. We just have to be very, very careful. We have to be very careful with the application of the three coefficients. Sometimes they can ask you about the coefficient of velocity, the coefficient of contraction, this and that. You have to be careful, know your formulas on each and every part that you're dealing with when you are dealing with an orifice. That is what you need to understand. All right, let's check another part, which was on 5.3. All right. So 5.3, they are saying water with a density of 1,000 kilograms per cubic meter flows through a tapered pipe with a diameter of, install the pressure, a smaller diameter, the velocity smaller. All right. So they were not given about how the pipe is. Is it vertical? Is it inclined? Is it horizontal? So you must be told how the pipe is given there. All right. So they were just going to assume this to be taken as a what? As horizontal. Since you're not given the head, like the pressure deep, the pressure heads that we are given, or the height that we are given on the inlet and the height at the outlet. Remember, when you are dealing with a horizontal tapered, you are going to see that on horizontal tapered, we have got the same height. So at the end, these heights cannot be mentioned on the question. So it means we're going to assume this to be a horizontal tapered, but they are supposed to mention this. Is it horizontal or vertical? Anyways, I talked about these on the introduction, so make sure that you watch the introductions about these pipes, the horizontal, vertical, and the one that is an angled, which is at a certain angle, using the laws of your Bernoulli's theorem. So we're given the density of water, the larger diameter 400 millimeters, the smaller diameter 200 millimeters. All right, so this is what we have. In this case, we have got the density of water. I'm just going to use this diagram, the density of water at 1,000 kilograms per cubic meter, like that. Then we are given the diameter in this case at the inlet. So take note here, this is the diameter that we have, the larger one 400 millimeters and the smaller one 200. So you just divide by 1000 to convert to meters. So meaning to say at the inlet, the diameter will be 0.4 meters. At the outlet, the diameter will be 0.2 meters. All right, then the other thing that you are given is that the pressure there on the smaller, where the smaller diameter is, the pressure is 16 kilopascal, and also the velocity there where we have a smaller diameter is 20 meters per second. So we've got the pressure at the outlet, which is P2, and the velocity, which is 20 meters per second. We do not have the pressure at the inlet. So that is, we're going to take this, find the pressure at the larger diameter of the pipe, and the pressure of the larger diameter of the pipe is the one at the inlet, which is our P1. So that is what you're going to need. So like I said, since you're not given the heights, we are going to assume this to be horizontal, because on a horizontal, the heights are the same. So if H1 is equal to H2, it means on your formulas, there's no need for you to consider that H. All right, so this one is just a repetition. I had this on the introduction, and I also talked about the relationship that we had in velocities, this and that. All right, so from your Bernoulli's theorem, you're going to see that P1, the pressure, is over the density times gravitational acceleration, V1 squared, over 2g plus H1 is equal to, this will be P2 over density times gravitational acceleration plus V2 squared over 2 times gravitational acceleration plus H2. This is what you're supposed to have in actual sense. So if you're to consider this, H1 and H2 are the same. I explained this, so there's no need even for us having this. So we want to calculate P1 is the one that we do not have. And also we do not have V1 at the inlet. We have got V2 at the exit. V2 is there, and also P2 is there. Remember, I talked about the formula that can connect the velocities, the velocity that we have at the inlet, and also the velocity at the outlet from the flow rate. All right, so I'm just going to quickly have this, but make sure that you watch the introductions. I said from the flow rate is the same. Q1 is equal to Q2. So from that, if Q1 is equal to Q2, is going to be like this. The area at the inlet times the velocity at the inlet is equal to area at the outlet times the velocity at the outlet, whereby the area at the inlet is taken from the bigger diameter, which is pi d squared over 4 times V1, is equal to the area at the outlet is from the smaller diameter, which is pi d squared over 4 times V2. So it is, when you are given V1 or you're given V2, you can calculate, and like here, you are given V2. So you can take advantage now to calculate V1 from there. So it means to have V1, I'm simply going to divide by pi d squared, like what you can see. So V1 is going to be equal to pi d squared over 4 times V2, everything over pi d squared over 4. So you're not supposed like to have these interpretations, guys. This is just for you to understand, but you're not supposed to like remanipulate this. If you understand these formulas, then you're not going to have a challenge there. So this will be equal to V2. So that will be V2 times d squared over d squared. So like, as you can see that if you're calculating V1, which is the velocity here at the inlet, that is our V1, it corresponds with the diameter at the outlet, all right? So you are calculating V1, use diameter at the outlet on top. If we are calculating V2, we are going to say V2 with the diameter at the other part, which is at the inlet. So you just oppose V1, oppose. So if you can memorize this, it can be of advantage to you. Yes, you can use that flow rate. Like I said, guys, make sure that you watch the introduction. I explained all those formulas. As for me, I'm just going to use this one. It's an easier formula. All these manipulations, you're not supposed to do them. I also talked about this on the introduction. We're not supposed to do this. We're just supposed to write the formula. Okay, I need to calculate V1. What am I given? I'm having V2. So it's going to be V2 times the diameter squared on the opposite one to V1, which is d squared of the smaller one, over the diameter where V1 is squared. Just like that. Just like that. You're done. So you don't even need like, okay. But for the case, for the sake of revision, I think we all understand what this is coming from, or where this is actually coming from. So that's our V1 there, which is going to be V2. V2, we already have this velocity of 20 times d squared, which is the d the smaller one, 0.2 squared over d squared, the bigger one. At the inlet, the bigger diameter is what? 0.4. So that's it. That's going to have the velocity at the inlet in meters per second. So that was going to give us 5, just 5, guys, 5 meters per second, just like that. So with the velocity of V1, we are able now to calculate P1, because that was the missing value. Everything was there, the density, everything is there. So we're just going to insert our values. P1 is the one that we are supposed to calculate, given the density of water of 1,000 kilograms per cubic meter, the gravitational acceleration of 9.81 plus V1 squared. We calculated V1, our velocity there, it was 5. So it's going to be 5 squared over 2 times 9.81. Remember, H1 and H2 are equal, so just eliminate that from your equation. P2 is the pressure given at the exit, which is 16 kilopascal. That's 16,000 Pascal over the density of 1,000 times 9.81, plus the velocity at the exit, which is where we have a smaller diameter. The velocity there is 20. So that's 20 squared over 2 times the gravitational acceleration of 9.81 plus H2. H2 and H1 are the same, so they canceled each other there. So meaning to say, this is what you just have at the end. So you can simplify this, like I said. Yes, you can have it as a decimal, that part, but as for me, guys, I love like just multiplying these two. 1,000 times 9.81. You have like answers which are fine there. This is going to be 9,810 plus, then just simplify this part here. 5 squared over this, 2 times 9, so it's just going to be 1,274 equal to the right-hand side. Simplify everything on your calculator on the right-hand side. This is going to give us something like 22.018. So that's it. Let us try to calculate our P1, transposing the 1, this value to the other side of our equation. We are going to have P1 over 9,810 is equal to, so this will be a negative because it was a positive. So it will subtract 1,274. You're going to subtract this value. So if we subtract, thus we are obtaining the value of what? Thus we are obtaining the value of, the difference, not the value of what we want, like what I wanted to say. We are obtaining the difference there. And that was going to be 20,744. Then you're going to cross multiply because this is the same as over 1. So this multiplies here. This multiplies here. So it's 1 times P1, which is P1. And that will be 9,810 times 20.744, which is going to be 20,000. No, that is 203,498.64 Pascal. Okay, that's it. You can divide by 1,000 to convert to kilopascal. That will be 203.499 kilopascal. All right, so this one is up to you. Do you want to change it or not? Not. All right, so as you can see, we had a lot of things to consider, which was fine. It was a nice question. Check the introductions. You see that this one was just a repetition of everything that we actually had. They actually just changed like values, but everything is just one and the same thing. 8 marks for that, guys. It's a lot of marks that you see there. A lot of marks in exam. All right, question number 6. Name 4 mean fluctuating loads on bearings. All right, the fluctuating loads, there is the linear. So there we have got the first part, which is the linear fluctuating. We have got the linear fluctuating load. We also have the fluctuating stepped load, the fluctuating. All right, guys, you're going to have the fluctuating stepped load, which is also another part to be considered. That's a stepped load. We also have a sinusoidal, fluctuating load. Then we, as a sinusoidal, then we also have a continuously fluctuating load. So we have got a continuously fluctuating load, sinusoidal fluctuating load. All right, so these are the types of the mean loads that we have. calculate the tensile force of each of the bearing. All right, calculate the tensile force of each of the bearing. If a single V belt, that is the number of V belts, it's just a single V, drives a power of, so you're given the power of the V belt. All right, this is like we are back to our belt drives there. Why are they doing? Okay, it can be like that actually. We're back like to our belt drives because we are given that a hint there. The total tensile force on each bearing is given by this formula. That is how you calculate the total tensile force. So you're given that we are supposed to calculate the tensile force. All right, we are supposed to calculate the tensile force, which I'm just going to call it T, the tensile force. And we are given the formula for that, that is supposed to be T1 plus T2 over 2. So the tricky part is you're supposed to calculate T1 and T2 from the tight side and slack side. So there they gave us the power, this and that, meaning to say we're supposed to use the information of those belt drives. All right. The number of V belts is a single V belt, so N is 1. Transmit power, so the power transmitted is 140 kilowatts, which is 140,000 watts. Then at the speed, which is the speed is 1,500 revolutions per minute. And the belt tension T1, we've got a relationship between T1 and T2. Thus T1 is equal to 15 T2. This is the relationship between T1 and T2. So it means if I can calculate T2, I can calculate T1. So the question was calculate this one, T, which is the tensile force, which is the total tensile tension, the total tensile tension that we have. So we need T1 and T2. Then we use this formula because we are given already the formula for this. But where are we going to have T1 and T2? Because that's what we need. We're going to need to calculate what? T1 and T2. So this is what you're going to need first. Calculate what? Calculate T1 and T2 first. So where are we going to have T1 and T2 from what we're given? All right, we are given power. This is a V belt that we have. So we can think of the effective tension because the effective tension is the difference between T1 and T2. So if we have the effective tension, at least we can think of calculating T1 and T2 from the, it's a lot. Let's just consider our steps. Let's just consider this. The power is given, if you're given the number of V belts, it's going to be the effective tension times the velocity times the number of V belts. That's how you're going to calculate our power there. So meaning to say, in this case, to have this effective tension, you're going to calculate by the velocity times the number of V belts, velocity times number of V belts in this case. All right, that's the effective tension that we want, which is the power is given. The power is 140. So this is 140,000 watts. Everything over the velocity. Remember, we are given the speed. We do not have the tension. So in that case, our velocity is going to be given by pi dn. So velocity is equal to pi dn over 60. So take note. But we are given. All right, guys. We need this velocity. We're going to calculate this V. No problem. From the speed of 1,500. All right. No problem. No. There's something that no. There's something that I did not take. All right, this is me. Because I'm considering say my working is different. All right. This was not reps per minute. I do not know that because it can be like that. So it can be, you can be given meters per minute. All right. If you're given like that, it means there is the velocity in meters per second. They do not want us to have many calculations. According to this unit, it's meters per minute. Meters per minute. So there it's not V. I took it wrong there. It's not any like this. This is revolutions per minute. So this one, it is the velocity V, which is 1,000 there, meters per minute. It's meters per minute. So as we need meters per second, so meaning to say, we're just going to divide by 60. So this one, to find the velocity in meters per second, you divide by 60. So this one is going to be 1,500 over 60. And that will give us 25 meters per second. So we have the velocity there according to the unit that you're given, that is meters per minute, not revs per minute. If it was revs per minute, we're going to use this formula, but that one is not revs per, it's meters per minute according to what you're given. So meaning to say already the velocity is there. All right, the velocity is there. So the velocity is there unless they made an error there, but according to what is written, that is how you're supposed to take it. So this is your velocity, which is 25 there. So that is 25 times the number of V-belts we're just given, that is, it is 1 there. So that we are going to get the effective tension. Actually, they were supposed to do this because we're going to have a lot of calculations there. So this is 5,600 Newton. So we have, in this case, remember we want to calculate T1 and T2. That is the major part of this, is to calculate T1 and T2. Now that we have the effective tension, let us substitute into this because we say the effective tension is equal to T1 minus T2. All right. The effective tension is equal to T1 minus T2, and we have the effective tension in this case. So 5,600, our effective tension is equal to T1, and we are given that T1 is equal to 15 T2. So it means we are going to have T1, which is 15 to, in place of T1, we're going to substitute the equivalent, which is 15 T2 minus T2 like that. So that's 5,600 is equal to 15 minus 1, which is 14. So we've got 14 T2 divided by 14 by 14. We are going to obtain T2 in this case. All right. So that is what you're going to have in this case from our calculation. And that was going to give us 400 Newton at the end. That is your T2. As you can see, we calculated the tension of the slack side. So meaning to say we can calculate the one for the tight side because there is a ratio there. T1 is 15, T2. So meaning to say we can calculate T1. All right. So to find T1, T1 is equal to 15 T2. That means our T1 is going to be 15 times T2, which is our T2 is 400 Newton. So that means you can calculate your T1. 15 times 400 was going to give us 6,000. So this was going to give us 6,000 Newton, which is our T1, the tight side. So these two are enough to give us what we are being asked in the question, because the question there was not about the effective tension. No, the question needs us to calculate the tensile force, and the total tensile force was given by the formula of a bearing. This one, T1 plus T2 over 2. So we are simply substituting because we calculated these values before. So what is it that we calculated? We're just going to substitute here. So that means T1 is T is going to be equal to T1 that we calculated. Remember our T1, it was given as, we calculated our T1, 6,000 Newton. All right. So this is our T1, which is 6,000. So I've got 6,000 Newton plus T2, which was 400. Remember, this was 400, and everything you divide by 2 according to the formula that there is a formula there that you're given. So you're simply using the formula that you are given there. So this was going to give you 3,200 Newton. So that is how you could have calculated this tensile force that you're given, which is the total tensile force of the bearings that you're given there. So that is it. 8 marks. That is a lot that you're going to have in exam. It was actually 7 marks. So this is 7 marks, as you can see. So you needed this information. You're going back to your belt drives to consider those formulas. Remember your formulas from a belt drives. Then use this formula because we never had used this formula. This one is for the bearings now, for the total tensile force. So that was the only new formula that we had. Otherwise, the rest, it was just something that we are used to in our calculations. All right, then on 6.3, we are given that a deep groove ball bearing, take note, it's a deep groove ball bearing. This is very, very important when you are calculating the expected service or life of a bearing. All right, so we are given that it has a radial load of 4,500, which is applied in this case, and the rotational speed of the bearing being 1,000 revolutions per minute. This is revs per minute, take note this time. All right. then the basic dynamic load rating obtained from the bearing manufacturer's table is the dynamic equivalent bearing load is 4,500 Newton. Calculate the expected life service, the expected service life of the bearing in hours. That is what you're supposed to calculate there. So take note, this one is a deep groove. So it follows that from the formula that you calculate the expected life, which is 1 times 10 to the power 6, you have this formula from your formula sheet, which is 60 times n, which is our speed in revolutions per minute, times CR in this case, which is our basic dynamic load to the equivalent dynamic load of PR to the exponent of P in that case, which can be determined by being a deep groove, or it can be a roller bearing. So if you're dealing with a deep groove or these roller bearings, P is taken to be equal to 3. This one is a deep groove. So meaning to say our P is equal. It depends with the formula that you use, but according to formula sheet, that is what we have there. All right, so you're going to use 3 for this one. So what else do we have in that case? Remember, the speed is given 1,000. So N is given 1,200 revolutions per minute. This time is revolutions per minute, guys. All right. The basic dynamic rating, which is our basic dynamic rating, is given as 4.2 kilo Newton. So that's our CR. It's just going to be 448.2. So if you multiply by 1,000, it is going to be 48200, which is in Newton. Then also the dynamic equivalent bearing, which is our PR 4,500. So the dynamic equivalent is 4,500. Take note of the units supposed to have same units there. So they wanted to test you on that kilonewton there. So that's it, everything we have. And I said for deep groove, P is going to be 3. So that means our life expectancy is going to be 1 times 10 to the exponent of 6 over 60 times the speed in revolutions per minute, which is 1,200. So this is 1,200 times our CR, which is 48200 over 4,500 to the exponent of what? To the exponent of 3. So this was going to give us the answer in hours, which is going to be 17,067,546 hours. That is what you're going to have at the end. So as you can see, guys, we have to be very, very careful in our simplifications. Very, very careful. So that was supposed to be 15 marks on everything on question number 6 on the bearings part. All right, so let us check the other part of our question, which is on question number 7. On question number 7, we are given a shaft with a diameter. It rotates with a bearing of this coefficient of friction between the contact surface, the radial force exerted. This calculate the circumferential speed. So this one, it was like a basic part, just like our science in our science N4, guys. We're back to dynamics there. That is the type of question that you're given. I want you to understand this, guys. This back to your science N4 there. A shaft with a diameter, we are given the diameter of the shaft. That's 0.08. If you divide by 1,000, 0.08 meters. It rotates at the speed. You are given the speed of rotation, revolves per minute, within a bearing. The coefficient of friction, there we have got the coefficient of friction, which is 0.04. The radial force exerted on the shaft bearing is 30 kilonewton, which is the force is given there as 30 kilonewton. And the radial force is the force that is being applied like this. So it's just like a normal reaction force, the normal reaction force. All right. So this one, the radial force is actually the normal reaction that is being applied. All right. So there we are given which results is frictional. All right, which results in a frictional loss. So because of this, there was a frictional loss, this and that. Calculate the following: the circumferential speed in meters per second, which is V. So that is the velocity, the speed in meters per second. So they want us to calculate V. Guys, we've got N speed in revolutions per minute diameter. How do we calculate V? All right, like I said, this one, it was just a normal application of our formulas. V, remember, that's pi dn over 60. That means we're going to have pi times the diameter, 0.08 times the speed, which is 400, everything over 60. So if you do this, we are going to obtain the velocity in meters per second, which is 1,676 in meters per second. All right. Then the frictional force, we have got the normal reaction there. So you can calculate the frictional force because this F, which is our radial force, is the normal reaction. And we also have the coefficient of friction. So like I said, guys, you can also relate from your engineering science, those calculations that you had from your science, N3, science N4. Remember, we had this condition that the coefficient of friction is equal to the frictional force over the normal reaction, and our normal reaction is the radial force of the bearing. So that means we can calculate the frictional force. The frictional force is simply the coefficient of friction times the normal reaction, which is our radial force. So that means our frictional force at the end was going to be the coefficient of friction, which is 0.04 times the normal reaction, which is our force that we are given of 30 kilonewtons. So you're going to multiply by 30 kilonewton. Since this is in kilonewton, it means our answer also is going to be in kilonewton unless you multiply by 30,000. So this was going to be 1,2. So like I said, we used the kilonewton. So it means our coefficient of friction is going to be also in kilonewton. Just like that, guys. This is your science N4, science N2 actually. The power loss due to friction. The power due to friction. There is a frictional force here. There is also velocity. So you can calculate power because power is a result of what? The force and the velocity. So since this is loss due to friction, it means we are supposed to use the frictional force. So the power is simply force times velocity. That is the formula for power, force times velocity. So since it is the power due to friction, we're going to use the frictional force. So that means our frictional power or the power against this force that we are going to have, the power against friction is going to use the frictional force. All right. So if we use kilonewton, it means our answer is going to be in kilowatts. If we use this in kilonewton, so that's 1.2 kilonewton times the velocity. We calculated the velocity 1.676. So guys, this was, they just maybe were tired with these questions, then they just wanted us to refer back to our science and N3 for revisions. All right, so that was going to give a 2,011 kilowatts as the power, which is the power against or the power to overcome this friction. That is what it can be like. All right. 7.2 we are given again to calculate the power. So this one again, it was a repetition. 7.2, calculate the power in this case. The power consumed by the following 7.21, a shaper operation in which the cutting force is 850 and the stroke length is 180 and takes 6 seconds to complete. So we are given force, length, and time. How can we calculate the power? How can we calculate the power? All right, so let us consider our formulas in this case. So the power from the force that we have in this case. All right, there we are given the distance and the time, so we can calculate the length or can calculate the velocity there. We can still use that formula for force times velocity, but it's going to be force times velocity, but this will be the cutting force. All right, so meaning to say the velocity can be calculated because there's the length, which is the stroke length. This is the distance. The stroke length is the distance. So it follows that velocity is this, the displacement or distance over time. So the displacement taken in meters, this is going to be 0.15 if you divide by 1,000 over the time in seconds. So time, meters over second, it means we're going to have our velocity in meters per second, which was going to be 0.025 in meters per second. So this is how you can calculate your velocity. So with the velocity that we have, now we can calculate the power because we have got the cutting force. The force is there. It's just like the previous case where we had the power, the force that we had from the frictional force. Now there's a cutting, it's a different force. As long as it is the force that we are using there, we can calculate the power. So the power from the cutting force, which is 850 Newton, times the velocity that we calculated, which is 0.025, we were going to obtain our power in watts. So this was going to give us 21,25 in watts. So then I think this is a smaller value that we can actually change to kilowatt. This is a smaller value. Just leave it like that. All right, then that's it. Let's consider 7.22, which is the lathe operation in this case. So there we are given the power again. We are still calculating the power. Remember, the question is calculate the power. So we still need the power, but of a lathe operating in which the cutting force applied to the tool is, there we are also given the force. So we are given the force, which is 750 newtons. Sorry for that. The speed is, all right, we are given the diameter and the speed. Guys, this one, they just a repetition again because power is going to be force times velocity, but the cutting force times the velocity. But the question was, how do you calculate the velocity given the diameter in meters, which is 0.3 meters, and the speed? Remember, when it is like this, V is equal, that is where we use the formula for pi Bn over 60. So meaning to say, the power in this case, we could have calculated this from the cutting force times the velocity, whereby the velocity when given diameter and the speed in revolutions per minute is going to be pi dn over 60. So this will be our velocity in meters per second. All right, so that's it. The cutting force is given, which is the force of 750 times pi times the diameter. In this case, our diameter in meters, that's 0.3. All right, so we're going to use our diameter, 0.3 times the speed, which is 250 in revolutions per minute. So we divide by 60. This was going to give us the power, which was going to be 29,000, no, 2,900, so 2,945,243 watts. So if you check this last question here, the question, it was just about the power, like we are back to our science, the formulation of the power from force and velocity. But what are you given there? Power, it's force times velocity. But according to your information, how are you going to calculate the velocity? That's what they simply needed from that question. So these are the typical questions that you'll be given. As you can see, that's it, guys, on this question paper, November 2023 exams that we had, which is giving us a total of 100 marks. So as we have got this, we can use it as a tool of revision towards our exams that are ahead of time. But for now, that's it, guys, from Mason African Motives. Till we meet again.